Let me start just thanking you and thanking Legion Drilling for inviting me to deliver this webinar on the importance of sampling disturbance in geotechnical practice. I would like to start remarking the fact that this is a topic that most academics and practitioners take it in a very simplistic way most of the time, and overlooking important factors that may have negative consequences in geotechnical design. And my goal today is try to highlight those important factors that we normally overlooked in practice and in academia, and also discuss some room for improvement for practitioners in order to try to take on a few new messages that we are trying to promote at the University of Newcastle and also with some colleagues. So let me start with a rather negative quoting Professor Ladd, late Professor Charles Ladd from MIT, and also Professor Don de Groot from Amstead University in the US. They, in 2003, delivered the Casagrande lecture in the US, and Don de Groot in 2022 delivered the Charles Ladd lecture as part of the ASCE session seminars that they ran in the US. They both agree that back in 2003 and just 3 years ago, that the state of practice in terms of soil sampling has regressed over the years in spite of clear knowledge of best practice methods. And before to continue with this presentation, I need to mention that this presentation focuses mainly on soft to medium soil that can be sampled with standard pushed samplers. So they have recognized that the reason why we have regressed in best practice methods over the past years and decades is basically due to two main factors. The first one is the poor sampling methods we normally adopted in practice. And the second one is a consequence of the first one, which is a poor selection of soil parameters. So why this is happening in practice and also in academia? One clear example is these are those CT scans that you can see at the bottom of my slide. These are CT scans that we have done on Shelby tubes, and acknowledging the fact that Shelby samplers are the most common samplers used in Australia and in many countries worldwide. So what we have done over the past 15 years is that every time we finish a sampling campaign, we scan the tubes using a standard medical CT scanner in the university to see how and to try to assess qualitatively the sample quality of each of those specimens that we are going to test further. As you can see, these are two different Shelby tubes obtained from the same depth in the Ballina site in North New South Wales, in the National Soft Soil Testing Facility. Retrieved from 7.5 to 8 meters depth, and you see that those tubes that sometimes or most of the time we called undisturbed or intact tube specimens are in fact really bad quality, and they have cracks, they have vertical cracks, subhorizontal cracking, holes, fissures, cavities that we can't see in a standard in normal practice, because we normally don't have these testing methods like the CT scanner. But because we are testing this type of materials, which are really bad, highly disturbed, then the soil properties we obtain from the laboratory tests we normally run are not good quality. They are not representative of the in situ material. So if we just focus on the sampling techniques that we have available, we have two main different trends. We can have block sampling if the conditions of the ground allow us to do that, and also the sampling depth is not really deep. And on the right hand side, you see the tube sampling techniques. Within the tube sampling techniques, we have two main samplers available: the Shelby tubes or the open samplers, and then fixed piston samplers. In terms of the block sampling, we have the trial pits, if that's possible due to the excavation constraints, and also the block samplers. So Before moving forward, I'm going to give you my very first conclusion for this webinar. The first conclusion is, and I will try my best to highlight the fact that Shelby tubes are not by any means a good option for sampling soft soils. I strongly not recommend the use of Shelby tubes, and I know that sometimes these sound a little bit too strong for in practice, but I will try to give proper scientific justification for that statement. And then I will try to promote the use of fixed piston samplers. I'm not sure how common the fixed piston samplers in legion drilling jobs, but this is something that is becoming quite standard practice in Australia as well. And if possible, we do have the possibility to use extremely high quality block samplers, and I will try to highlight the capabilities and the operational principles of one option which is available at the University of Newcastle. And I'm going to start with that. I'm going to start with the block sampling techniques. So on the bottom left-hand side, you see a photograph of the mini Sherbrooke block sampler. This is a reduced version of the original Sherbrooke sampler developed in Canada in 1979. So the original Sherbrooke sampler required a 400 millimeter borehole in order to be used, and of course this puts some constraints in terms of the drill rig that needs to be used and the casing that needed to be used. Because of that, because of the original Sherbrooke sampler was basically used by academics in order to perform research on high quality block specimens, the NGI from Norway, the Norwegian Geotechnical Institute, decided to redesign the sampler, and now this is the option. The option has the reduced version has a diameter of 180 millimeters. To use it, you have to have a 200 millimeter borehole. Then the height of the sample that you can get is up to 250 millimeter, from which you can get several triaxial and odometer samples for laboratory testing. The maximum depth that where this sampler have been used is 25 to 30 meters, just because of the constraint of the drill rig, right? But there is no reason why we could not reach deeper depths. How this sampler operates? So we have, as I said, we need a 200 millimeter borehole. So the sampler itself is composed by a metallic cage that you can see here. They have annular slots or horizontal cutters on this side. I'm trying to indicate that with my cursor. And also at the base, we do have 3 bottom metallic blades, horizontal blades. In order to use this for sampling soft soils, the first thing we have to do is to open the bottom blades. So the bottom blades need to be open in order to allow the natural ground to get inside this metallic cage. To do that, we use these bolts that are located at the top of each column, and then we can move or we can rotate those blades before the sampler is connected to the drill rods. So once the bottom blades are open, now we connect it to the drill rods and we lower down the sampler to the required sampling depth, and we have to rotate it at normal speed. It's preferred to rotate the mini Sherbrooke at very low speed, and that's controlled by the drill rig. So the rotation starts, and the annular slots start to carve laterally the soil around the bottom of the sampler until we reach the maximum height that we can reach with this sampler, which is 250 millimeters. Once we reach that depth for our block sample to be retrieved, we need to stop the vertical movement with the drill rig from the ground surface and keep rotating horizontally the sampler in order to remove all the mud from the block. And in order to maximize this operation, this sampler includes also water jets. That water jets are connected to the base of the block, to the base of the sampler, sorry, and then we can inject water pressure in order to wash all the mud around the cutters. So after 5 minutes of keeping the sampler rotating at the base, then we need to activate those bottom blades. How we can activate that? We need to basically drop a big weight of big mass from the ground surface, which is connected to the drill rods, and that metallic mass is going to impact these pieces at the top of the sampler, which they are going to activate those springs that you can see here. These springs are going to activate the horizontal closing of these bottom blades. So those springs are going to nicely and gently start to move the blades from the outside of the sampler towards the center. And at the end of this operation, the base of the sample is going to be cutted, fully cutted, and these 3 blades will serve as a support for the sample, for the block sample to be retrieved to the ground surface. The sampler that we have at the University of Newcastle was initially used by Black In Situ in 2021, as you can see in the photo on the right-hand side, to sample tailings. And we have also used it for sampling high-quality soft soil specimens from Ballina site in North New South Wales in 2024 and 2023 and 2024. Highly recommended. Is not that difficult to use, and we can provide some guidance if any industry partner is interested in using our sampler and then buy their own one. These are photographs about the quality of the specimens that we can get with the Shelby sample. Those at the top left-hand side are really complicated deltaic deposits from Barcelona in Spain. We use the original 400 mil Shelby sampler. This is a really complicated silty material, but we managed to get really high quality specimens for sampling and laboratory for testing and in the University Polytechnical de Catalunya in Spain. So the second photo is a photo of one of the blocks that we got in Ballina in 2014, for which we hired operators from NGI in Norway. But after we bought our own sampler in 2016, and Black In Situ has developed some skills in order to operate this sampler, and now is becoming a little bit more common in Australia. So after you retrieve or you cut the block, you have to cover it with plastic film, aluminum foil to minimize moisture losses, and then you cover it with plastic in order to minimize vibrations during transport. And we normally place them in sealed containers, plastic containers that you can see here in blue. And if you want, you can also wax them in order to store them for a long time. We have retrieved 40 blocks. We retrieved 40 blocks in 2014, and we have been testing them over the past 11 years at the University of Newcastle. We haven't noticed any changes in moisture content or any oxidation in around 10 years, which is really good. In terms of the tube sampling, so before describing briefly, I'm pretty sure you have more expertise in describing the elements that compose all the samplers that you use in practice. My point here is more about what are the processes that are involved in the tube sampling campaign. So when we run a tube sampling campaign, we have to first drill a borehole, and this induces a stress relief, as you can see in this sketch on the top left-hand side. The stress relief takes place mainly in the vertical direction, but also in the horizontal direction in the ground. Then we normally push a Shelby tube into the ground, and this push must be quick because we want this operation to remain undrained. Therefore, because it's undrained, there is no volume change, but there is a potential excess water pressure that may or may not induce sample disturbance inside. After that, which in my opinion is one of the most complicated operations in this technique, is we need to retrieve the tube with the sample inside. And if we use Shelby tubes, what happens is that we create, when we try to pull the tube sampler from the ground, we create suction at the base of the tube, because we need to cut the base of the soil inside the tube, and we need to disconnect it from the natural ground. That pulling induces suction at this point at the base, which basically induces water redistribution inside the soil. Therefore, we are changing the natural water content in the soil and therefore the density in our specimen. And we don't know by how much this suction is affecting our soil quality. After that, we got the sample in the ground and we need to seal it to minimize moisture losses. And we normally use melted wax. To protect the sample, we put melted wax on the top and bottom ends, as you can see in this sketch at the bottom left-hand side. But wax must be liquid or semi-liquid, and that means that the wax induces a thermal gradient that travels from the tube two ends towards the center of the sample, inducing most likely an excess water pressure in the case that there is no volume change. In the case that we do have volume change inside the soil, because you have cracks, you have cavities, then we have also soil deformation here, and this changes the density of the natural soil that we want to test further, and from which we want to obtain soil parameters for geotechnical design. Transport and sample storage. We normally promote the option of keeping the tubes vertically aligned, not horizontally aligned, in order to avoid the natural soil inside the tube to flow. And we have seen quite a few examples of tube specimens that are transported and then shipped to the lab in the horizontal position. And then when you try to open them up, basically they flow like a toothpaste, because there are some cavities and the soil is allowed to move inside, and that's not good. This also induces some negative changes in the natural structure of the soil. When we transport our tube samples, we normally place them in sealed containers similar to the one we use for block specimens. We place between 10 to 15 in one of these barrels, and then we place them on top of a layer of wet sand. The intention here is to maintain inside this container a really high relative humidity to minimize drying from each tube. So the wet sand is a really good option. First, because minimize vibrations at the base, and second, maintain a really high saturation degree in our specimens. We also put some polystyrene strips just to minimize vibrations between the tubes. Finally, in the lab, we need to strew the soil for laboratory testing, and that sketch at the bottom right-hand side is something I have seen in many labs here and worldwide, which is using the hydraulic jack to push it out, like in a toothpaste. This is a really bad option for if the intention is to run mechanical tests like odometers or triaxials for getting soil parameters for design. Why? Because when we use the flat jack, we need to overcome the horizontal friction, the vertical friction between the soil and the wall, and that is normally requires quite a lot of force, and therefore we have to compress the natural soil in order to push it out, and that is not a good procedure whatsoever. So I will discuss a few options later on. So, but what is happening when we run a tube sampling campaign? This is the interpretation from late Professor Charles Ladd and Don de Groot in 2003. So the soil at in situ state is located in position 1. If, under ideal conditions, if we were able to test the soil in situ without taking any sample under triaxial conditions, running a K-node consolidated and drain compression test, without taking the soil from the ground. If you imagine that we can place a big triaxial machine inside the ground and then run the undrained triaxial test. If we were able to do that, the stress path followed by that sample will follow this path from point 1 to point A, right? So we all know that because the natural soft soils are slightly over-consolidated, then this generates positive excess pore water pressure during undrained shearing, and therefore the mean effective stress reduces, and the maximum deviatoric stress or undrained shear strength that we could get will be indicated by point A here. However, we can't do that. So what we normally do is we basically drill a borehole, then push the tube sampler inside the ground, and we have to pull the sampler from the ground, then seal it, transport and store that, and then extrude the soil from the tube in the lab, and then prepare the sample for laboratory testing. All these activities, from drilling the borehole and then pushing the tube inside the ground and then pulling it, basically induces this very complex stress path from 1, 2, 3, 4, 5, 6, 7. And at the end, when we extrude the soil in the lab and then we cut it for UCS test or any triaxial test, we are located here at 0.9. So this 0.9 has nothing to do to 0.1, which is the in situ stress condition that we want to preserve, right? And this is one really serious problem. But the more important problem is then the labs basically normally decide to run UCS tests or unconfined undrained testing, right? Because it's cheap and it's quick in order to get the undrained shear strength. If we do that, the stress path is this stress path from 9 to point B. And this point B is far different from point A. So we are largely underestimating the undrained shear strength. So this is definitely not good for our design if we want to represent the natural ground conditions. But more importantly, if you pay attention to the stress path from 9 to B and compare that with the stress path from 1 to A, they are totally different. In fact, when we run a UCS test, the stress path move from the left to the right because of the highly overconsolidated clays, because this sample at 0.9 is highly overconsolidated. Highly overconsolidated clays develop negative pore pressure. That's why the stress path move from the left to the right rather than from the right to the left. So let's discuss briefly what is the disturbance coming from different sources. So the first and the more important disturbance that has been identified is the mechanical disturbance due to the penetration of the tube sampler into the ground, right? So this is a really old problem in soil mechanics. I'm not saying that this is something that we have recently discovered by no means. This was originally discussed by Borslev in potentially the Bible in situ testing back in 1949. So Borslev and many other researchers came up with a 500 pages book or guideline, and they proposed geometrical descriptors in order to minimize sample disturbance in practice, in order to improve the reliability of the soil properties we normally obtain from those samples. So they proposed a few descriptors. The first one is the ratio between the external diameter. You basically need to be referred to this sketch on the top right-hand side. D is the external diameter of the tube sample, the Shelby tube, if you want, divided by the thickness of the wall. So this ratio controls largely the sample the soil disturbance inside. So if we have a very large ratio between DE divided by T, then that is going to reduce the sample disturbance inside the ground. Another factor that they identified is the area ratio AR, which is the difference of the external and internal diameters, as you can see here, but the diameters are squared here. So if we have a very low area ratio, that is going to minimize sample disturbance, which is good. Another factor that they identified is that in the old days, we used to have different diameters at the toe of the sampler with respect to the diameter in the center of the sampler. So we used to have some sort of clearance for the soil to relax laterally inside the tube once was inside the tube in the middle. So that's called the inside clearance ratio, and this is really, really, really bad in order to produce sample disturbance. So the idea is to have inside clearance ratio basically close to 0 or equal to 0. No difference in diameter between this point at the cutting shoe or in the middle of the sampler. Another factor that controls the sample disturbance is the cutting angle at the shoe of the sampler here, beta. So that angle should be kept as minimum as possible in order to minimize sample disturbance. And Borslev back in 1949 also discussed the positive impact of having an internal piston in order to minimize sample disturbance. So in 2003, late Professor Charles Ladd and Don de Groot proposed this simple table that we should use in practice, and this is part of the ASTM standard for sampling techniques in America. So in order to choose or select Shelby tubes, we should use Shelby tubes with DE divided by T larger than 40, with area ratio lower than 10%, inside clearance ratio equals to 0, no difference between this diameter here and in the center, and angles for beta around 10 or less than 10. I have to say that angles of beta lower than 10 are dangerous for the operators. It's too sharp and they can create some problems, but angles of beta around 10 to 15 are pretty good. So what happens with the open samplers with the Shelby tubes is that we have here on the left-hand side the sketch, how the operational principle of that. We push the sampler into the natural ground, and there is nothing inside to prevent any entrance of mud or remolded soil into the sampler, and that's the main problem that this sampler has. And then we have some vents for all the water inside or the mud to basically flow out. But as I have discussed before, if you check this CT scan for another Shelby sample we have tested in our lab, you see that there are in almost 99% of the cases that we have seen in our lab, Shelby tubes are really bad quality when you scan them, when you see through them, and you see vertical cracks, subhorizontal cracks, also fissures and cavities. And the problem with these is that the Shelby tubes are the most common sampler used in Australia, and we have been trying over the past decade and a little bit more to push for a change, talking to practitioners like you guys and talking to RMS, now Transport for New South Wales, in order to modify the guidelines and recommend something else, recommend the fixed piston sampler that I will discuss in a minute. But why this is just a qualitative assessment of sample disturbance. We have done also a little bit quantitative analysis. In one of the PhDs I have supervised in collaboration with the University of Western Australia, we used the centrifuge strong box that you can see at the left-hand side in order to see through the soil and through the sampler during the penetration of a standard Shelby tube into the ground. So in this case, we tested a calcareous silt from the northwest shelf. And what we did was, if you see that the centrifuge strong box has a transparent windows. So this is a top view on the right-hand side. So you see this is a transparent window in this part, another transparent window in the other end. So what we have done is we took a Shelby U50 and we split it into two halves, and we push one half against the wall in order to see what happens outside the tube and inside the tube, to take photographs in order to see how much disturbance this operation induces. And also we were able to pull it from the ground to see what is the influence of this. So we focus on two things: same sampler diameter, which is the U50s. I strongly don't recommend use Shelby tubes lower than or with a diameter lower than 63 millimeters, because 63 is already borderline, 50 is really bad. So anyhow, so we use Shelby tubes 50 millimeter in diameter. So we maintain the same angle beta, but then we change the area ratio, and we also change the ratio DE divided by T, which is the recommended value from Charles Ladd and Don de Groot. So the upper one, which is called TNPD, is the thin Shelby tube. In theory, the good one according to the recommendation by Charles Ladd and Don de Groot. The second one, which is TKPD, is the thicker one. So is basically a standard one in which the area ratio is larger than the recommended value, and the ratio DE divided by T is far lower than the recommended by these two authors. So what I'm going to present here, this one on the right-hand side, are the shear strength contours that we obtain after taking images during the penetration of the sampler. And then we use a particle image velocimetry technique that is common in academia to estimate displacement vectors and then this strain contours in this particular case. So I'm going to just show you half of the tube because this is an axisymmetric problem. So you see the central line here, and the wall of the sampler is just indicated here by this dashed line. I'm just indicating with my cursor. So the contours, and you see the numbers in there. Inside the tube, you see contours of shear strain up to 20%, 18%, 16%, very close to the wall. And then close to the center, we have shear strain contours of 2, 4, 6, even up to 10%. And this is the thick sampler. So this is something that you may expect, that the thick sampler, Shelby sampler, is going to induce large deformations inside the tube. What happens with the thin sampler, in theory, is recommended for practitioners. So although the numbers are a little bit lower, there are still a lot of shear deformation happening inside the tube. You see the wall is located here. And then we have lower values, but still quite large for soft soil. So we have close to the center 4 to 6% shear strain, which is quite large. So by no means the thin Shelby sampler is inducing no disturbance. So this is already bad enough, and then practitioners should try to move on towards a different technique. But this is just during the penetration. What happens during sampler retrieval? So these are photographs for the sampler retrieval. You see that the tip of the sampler is located here, indicated by these two white arrows. And this is the point at which we started to pull up, and then you see some kind of shear plane developing at the base. Then this movement, this pulling, induces heave at the base of the ground because of the suction between the soil inside the tube and outside in the natural ground. And then we keep pulling, and we realize that the tip of the sampler is moving faster, and then the sample is just holding there. So there is some part of the bottom of the specimen is just hanging in air because the tip of the sampler is moving faster compared with the movement of the soil, because there is some kind of internal slippage between the soil and the wall and the tube inside. So that creates some tension cracks. The tip of the sampler is now here, and because of the self-weight of this part of the tube, so that we are losing this bottom part of the material, and then this is the recovered sample that we got and we are going to test. So by no means these Shelby tubes or open samplers are a good technique. How we can minimize this influence? But we can include an internal piston in order to minimize this disturbance. So the sketch on the left-hand side is the operational principle of the fixed piston sampler that I guess that you guys are familiar with as well. So this has two tubes instead of one external thick tube in which we are going to encapsulate an internal standard Shelby tube. But in addition to that, we are going to include an internal piston inside the Shelby tube here. So the piston is locked, is fixed at the base of the Shelby tube, and before the sampling is happening, before the Shelby tube is pushed into the natural ground. So once we achieve, or we reach the target depth, then we use hydraulic pressure in this internal cavity here to push this inner sampler head. This one is going to push into the ground the internal Shelby tube. And the piston is going to be locked from the very beginning, because otherwise we are going to just push the soil and we are going to get no soil into the sampler. So the piston is fixed at this position, and then the inner head is going to push downwards the Shelby tube into the natural ground. Once we reach the maximum length of the tube, the sampling depth, then we are going to lock the piston and we are going to pull up the sampler. The fact that we have the piston at the top, that piston induces some counterbalance the suction that is created at the base of the wall, at the base of the sampler, sorry. So this reduces the disturbance that is normally occurring at the top and bottom ends of the tube, and then therefore minimize the subhorizontal cracking that you have seen in the CT scans before. So this is a CT scanner for a fixed piston sample in Balina clay from the same depth that we took the previous Shelby tubes I just discussed before. You see that there are still some zones of the tube with a few cracking, but these zones are the top and bottom end, which is basically what is expected. So there is no way that we can reduce this sampling disturbance to zero, but using fixed piston samples, we reduce the disturbance in the central part of the tube, and also we only got some disturbance at the top and bottom ends, which is quite good. Just briefly, what happens after retrieving the soil and then sealing the sample? So we normally use wax, and we have studied carefully the influence of the waxing on sample disturbance. So this is a photograph of what I have seen this is a photograph that I took in Spain, but I have seen similar stuff in Australia and also in different countries in South America. So when we normally use wax, we need to melt the wax down and then pour the wax into the to cover the top and bottom ends. So this photo on the right-hand side you see is liquid wax. The operators in this particular case decided to include some plastic bag in order to separate the soil from the wax, which is not bad. Something that I noticed was that the temperature of the wax was around 80 or higher than 80 degrees, which is quite large. So the question is, what is the recommended temperature for the wax before using it for sealing tube specimens? If you check the International Manual for Sampling of Cohesive Soils in 1981, or if you check the Australian standard, there is no recommendation whatsoever about that. Nobody pays attention to that. There is a recommendation for the temperature of the wax in the ASTM standard and in this book that is quite useful, the book by Clayton in 1995. So they recommend that the wax should have a maximum temperature around the melting point, very close to the melting point, which is 55 to 60 degrees, not 85 or 90 degrees, because it's too liquid, it's too hot, and it uses a lot of thermal gradients, all right? So we have done some experiments in our lab in order to see what is happening inside the soil when we wax them. So we went to Balina, we took some tube specimens, additional tube specimens in Balina clay, and then we cut them into halves. You see that the maximum length for this sample is 250 mil. It's basically half of a standard Shelby tube, if you want to call it this way. And then we have waxed it under controlled conditions. We have put a cake of wax of 30 millimeters max. And then we have installed some sensors at the base, pore pressure sensors, which is the UW4, and thermocouples that also to monitor the temperature inside the soil, and also thermocouples attached to the tube wall. So we have also installed tensiometers. So 3 tensiometers, UW1, UW2, UW3, located at different depths in order to see what's happened. So what you see in the top, in the right-hand side top, is the temperature of the wax, which reached 80 plus degrees, and then the temperature at the same location here, but outside the tube. All right. So the wax was poured at 80 plus, and then the tube reaches temperatures around 50 degrees. And then what I'm going to show you is the evolution of pore water pressure and temperature at position UW1, UW2, UW3, and UW4. So this is the pore pressure in red for UW1, very close to the heating source. You see that we started with initial suction as is expected, and then at some point, instead of the pore pressure going up, the pore pressure is going down. And at some point, just go back again to the initial value suddenly, and then start to reduce again. Okay. So what happens at position UW2? Basically the same, slightly small. The magnitude is slightly smaller because the difference in location here. So we have this one was located 30 millimeters, the other one 60 millimeters, and the next one is 170 millimeters from the heating source. So UW3 more or less the same. So there is no important change in the trend. A little bit of change in the magnitude of the pore pressure induced, which is suction, as you can see here. And then the suction start to develop again after a while. So we will discuss a little bit later what happens in this sudden change in suction. And at the base of the sample, although it's 250 millimeter far from the heating source, we still have some the similar trend. The magnitude is much lower in here, but the trend is the same. So what is the reason for the suction to be developed and then the suction to be loosed at this point? The reason for this is that the wax is a quite interesting material that when you pour it and then the wax start to solidify, induce at the interface between the wall and the soil, the shape of the wax cake becomes concave. So it's basically that the wax is pulling up because of the concave shape of the cake in the contact, is trying to pull up the water or the sample, but the sample is so rigid that it doesn't move. So this induces some water movement or suction developed at all around the sample. So the solidification of wax is pulling the water upwards until the point where the cake of wax is basically fully solid, and then the wax cake detached from the soil. And that's why we have this sudden drop in the suction here. What is very interesting is that after this solidification of the wax, then the soil tends to keep going with the suction that has been previously induced during the solidification of the wax. So long story short, waxing is inducing water redistribution between the soil. All right. And how much impact this have on sample disturbance? It depends on the type of the soil, depends on how much variation in water content we have from the center to the ends of the specimen. What we normally use in our university, we normally, instead of wax the samples directly or put the wax in direct contact with the sample, with the soil, we use a foam plate, which is 10 millimeters thick, you can see here. And on top of that, we put the wax, the paraffin wax. And that minimizes a lot the thermal gradient induced by the wax into the natural soil. And therefore, we reduce sample disturbance a lot. Transport and storage, I have already mentioned that we try to keep all the tubes aligned vertically in order to minimize the flow of the soil inside. So a little bit more on sample preparation. Sample preparation is also something that is overlooked, in my opinion. We normally ask the technicians to take care of that without checking that the procedures are useful and are may produce reliable specimens. So at the top, you see some examples of soil extruders, basically pushing the sample out, which I have already said that is not good because the halation force is quite large and we basically compress the soil like in a toothpaste. We normally slice our tubes. We don't recycle our tubes. And this is something that sometimes is a little bit shocking for practitioners, but is the best way to prevent additional sample disturbance. So as you can see in these photos at the bottom of the slide, we slice the tubes. We use a mini grinder to just cut the tube. If we need to run a triaxial test, and the triaxial sample is 50 by 100 millimeters. Then we cut 150, 160 slices from the tube. To cut the tube, we use the mini grinder, and then we use the wire saw to cut the soil inside. So you see two examples of this process, and we also use stainless steel tubes all the time. We don't use this one at the bottom left-hand side is a rusty not stainless steel, and this was a test that we did it on purpose in order to check the chemical reactions that are induced by using those tubes. So once we have our slice ready, we need to push out the soil. At the bottom, you see what we have done in Ballina in our test on Ballina clay, because this material is quite soft, and if the tubes are not really, really old, the material inside, I mean, the contact, the soil hasn't developed any chemical reactions or bonding between the soil and the tube, and therefore you just need to put a small plate, a piston at the base, and then you just need to push a little bit with your hand, and then the sample is going to naturally stay there, and you will be able to slide down the tube without any problems. In the example at the top of the slide, this is more for medium to dense silty samples from Barcelona. And in these cases, the pre-consolidation stresses are higher than 200 kPa, and the soil is quite stiff, and we had to basically produce or design this extruder system, which is very simple. It's just the slice, we put it in the middle, we have a piston, and then we just use a load frame in order to push out the sample, and we just maintain it in a container, which is just an external tube that maintains this sample in place in there. So this is a sample, a photo of a sample that we have extruded with this method. So in that way, we minimize further the potential disturbance due to the sample preparation. The MIT back in 2003 proposed this method, which is after slicing the tubes as well, so you can use a wire saw, hypodermic needle, to penetrate into the soil and then break down all the bonding between the wall and the natural soil. So you can use the needle to break these bonds, or you can use the needle and then the wire, and then you can rotate the wire in order to break down all this bonding. That method works. We have used it a few times for shorter specimens, but for triaxial samples, it's very difficult to maintain the alignment of the hypodermic needle without cutting the soil. So we have decided not to use this one on a standard testing procedures here, but it's also useful if you have the right tools to do that. Time effects. So time effects, we have biochemical reactions produced by the influence of the oxygen or the contact of the samples with the oxygen. So these are examples about how the undrencher strength reduces with time for specimens of soft clay in the US, 1976. You see the undrencher strength reduces from 20 plus down to 10 kPa in 9 months. The pre-consolidation stress is also largely affected by the storage time. In Ballina, we have noticed almost no effect of the storage time on mechanical properties. So apart from these 2 points here, which we knew from the very beginning were largely disturbed specimens, these are tests we have done on fixed piston samples. So after 7 days of sampling, 1 month, then 1 year of testing. So the message is that if the material is highly plastic, if the soil is highly plastic, the effect of the storage time is minimal on the mechanical properties. If your soil is low plasticity, like the ones you can see in this photo, so there are this slide, we see results from quick clays in Norway, in Sweden, and also soft clays in different places. The trend for this storage time to induce an increase in this ratio delta E divided by 0, which is the sample quality index that I will explain in a minute, is basically more important in low plasticity clays. If your sample is high plasticity, you can store them properly and then test it after even 1 year or more than 1 year without too much changes in the mechanical properties you have previously measured. How we can evaluate sample quality, and this is potentially one of the key messages of my talk today. So there are two main trends. So we have non-destructive techniques, which are good because we want to check if the sample, our quality is good enough before doing any test. And I'm going to highlight only one, which is the image technique that qualitative and quantitative analysis we have developed at the University of Newcastle based on CT scans. But the more standard procedure is based on mechanical tests. So these tables at the base basically summarize the methods that you can have in practice. So the first table on the left is the original procedure proposed by NGI based on volumetric strain. I'm going to discuss briefly about the second table on the right-hand side. So people from NGI, Tom Loon and co-workers, proposed a index, a sample quality index, which is basically delta E divided by 0. We need to quantify how much is the change in void ratio required to recompress the soil from zero kPa, so after putting the soil in the equipment, and then reaching the in situ vertical stress. Okay, so if we can quantify this delta E, or the void ratio required to recompress the sample to the in situ stress, and then we normalize it by the initial void ratio of that sample, we can classify our sample quality in 4 main categories, depending on the OCR. If our samples are here, OCR 1 to 2, if we have this ratio lower than 0.04, our sample classifies as very good to excellent. If this ratio range between 0.04 to 0.07, our sample is good to fair, which is basically good enough for mechanical testing. But if this ratio is higher than 0.07, your sample is bad and really bad. So you should not use those results for design. And that's what you can get in practice. And this method works quite nicely. The main problem is that you have to run the test before and after the test, you realize if your sample is good enough or is bad. This is an example of using that method. So in Ballina, back in 2017 and 18, we took specimen using the Shelby sampler, the block sampler. We used the fixed piston sampler in red. We used two different, a free piston sampler, which is the P100 in black, and then the standard Shelby tube 75 millimeters. You see the compressibility curves from the odometer test. You see they are far different, particularly between the Shelby tube, which is this gray line, and the other samplers. The stars indicate the estimated pre-consolidation stress, and you see that the block sample and the fixed piston sampler gives you more or less the same pre-consolidation stress. The P100 gives us lower, and the Shelby tube gives us a value which is lower than the in situ stress, which is not possible. If we derive this compressibility curve, because this is a constant rate of strain test, we can get the evolution of the compression index with stress level. And you see that the compression index, because of the S shape, that is not linear for the block and for the fixed piston sampler, is highly nonlinear in this part. You have a CC that reaches values up to 3 in the block sample, up to 2.25 in the fixed piston sampler, and only 1.25 in the Shelby tube. Basically, because the Shelby tube has this basically linear compressibility curve. But the shape of the compressibility curve in high quality natural soft clays is highly nonlinear in this, close to the pre-consolidation stress. So Shelby tubes are not able to, those samples don't capture properly the compressibility of the natural soil. We also did some simple shear test. We recompressed the sample to the in situ stress before shearing. So you see that the volume, this is the compression under K-node conditions. So you have the block sample only requires 2% volumetric deformation to recompress to the in situ stress. The same for the fixed piston sampler. But if you use the Shelby tube, you need to recompress it up to more or less 9%. So large compression, therefore your sample is bad quality. But then when you shear it, the peak values under undrained shearing are not that different. But then this is a potentially misleading result. The reason is we have more or less the same tau peak here between the Shelby tube and the block and the fixed piston. The reason for this similar value is because the sample has been recompressed to the in-situ stress. If you don't recompress your Shelby tubes, then you are going to get much, much lower values under shearing. So recompression is definitely a good option, but still Shelby tubes should not be used because they don't reflect the real soil response. So we have used this index from NGI delta E by 0 for all these samples that we have tested. This is the pre-consolidation stress. According to this index, the only two samplers that provide us with good quality, excellent quality samples are the block sampler and the fixed piston. The free piston is more or less good in this case, and the Shelby tube give us very poor sample quality. The M modulus, the odometer modulus, the same thing. Only the block and the fixed piston gives us the high quality specimen, and the Shelby always gives us the very poor sample quality. In terms of the simple shear, more or less the same. So the Shelby tube gives us the poor sample quality. And if we estimate the strain at peak condition, you see that it's only required 2 or 3% for the block and the fixed piston to reach the peak value, whereas it requires a lot of deformation for the Shelby tube to reach the peak condition. So clearly, Shelby tubes are not good. The main problem with this method is you need to run the test, and at the end of the test, you realize if everything you have done is good or bad, which is definitely not good. So that's why we are proposing a different method. So this is a qualitative assessment of sample quality using CT scans. You see the two Shelby tubes. These are scans that I already showed to you both. You see all of these tubes has cracks and defects and cavities. In the middle, you see the free piston sampler. The free piston is better, but you see that there are still more subhorizontal cracking. The only one that has only cracking at top or fissuring at top and bottom ends is the Shelby tube. And therefore, the Shelby tube, the fixed piston sampler, sorry about that. So the fixed piston sampler gives you really good quality along the entire tube, except top and bottom ends, which is really good and good enough for practitioners to be using geotechnical design. So the way we have used it in a qualitative way is just sketched here. So we have the CT scan, and then we decide where we can trim samples for odometer test or CRS, and also triaxial test. And we can also detect that the presence of shells or cobbles or any other stone that you cannot test in the lab. So therefore, you decide for this tube only to run one triaxial and one CRS, and that's it. The other part of the tube cannot be used. What is the implication of sampling disturbance in geotechnical practice? I'm going to use one of the simplest examples that we got. This is part of Geomechanics 1 or any geotechnical soil mechanics 1 course, is the settlement analysis of embankments on soft ground. So we are going to keep it as simple as possible. So in order to analyze this in an Excel spreadsheet, you only need to use 1D Terzaghi consolidation theory, and then potentially find a different method to calculate the excess pore pressure. So if you check the Terzaghi's consolidation theory, these are the two equations you have to use. The total settlement for over-consolidated soil is given by the equation at the top, and the total settlement for normally consolidated soil is given by this equation at the bottom. If we use the finite difference method to estimate the evolution of pore water pressure that can be easily typed in an Excel spreadsheet, then we have this equation where we have this parameter beta and the CV as a input parameter from the soil. So in order to run this analysis, which is very, very useful in Australia because we have embankments for road and rails all the time constructed, this is a really simple way to do it. So we need to obtain 4 parameters from the lab. And I haven't discussed about creep in this. I'm not going to include creep, but C alpha is also a key factor here. So we need the recompression index CR, we need the preconsolidation stress or yield stress, we need the CC, and we need the CD to calculate the pore pressure. So what we have done back in 2018, we have collected those numbers from the test I just explained to you before, test done on block specimens on free piston sampler P100, on fixed piston sampler 090, and the Shelby tube U75s. You see that the numbers for each property change because the sample quality is different. But we have done this analysis in order to calculate what is the settlement estimated based on those parameters. So let's start with the block, which is the solid black crosses. So if we use the properties from the block specimen, we got a maximum settlement after 2000 days of 1 meter. If we use properties for the fixed piston, which is the open squares, we have more or less the same trend. Then let's go back to the Shelby. If we use the Shelby, we only have less than a third of the settlement predicted after 2000 days. And surprisingly, if we use the free piston sampler, which are the triangles in here, we got more or less the same thing, but the numbers are different. The reason for this kind of good agreement, which is not true, between the free piston and the block and the fixed piston is because the compensation between more or less the really low preconsolidation stress for this sample, 45, is compensated by the very low compression index here. So if you have very low preconsolidation stress, you are predicting very large deformations. Whereas the natural soil has a much higher preconsolidation stress, but also a very large compression index. So these two properties compensate to each other. By no means good practice, but it's just a matter of luck in here. Sometimes we got the right value for wrong reasons. So this is something we also need to keep in mind. So finally, I'm going to take the next 3 minutes just to explain a new approach we are proposing and we are trying to promote through practitioners. It's based on CT scans, but it's a quantitative analysis of that. One of my former PhD students, Dr. O Yang, has developed this app that you can use even without he developed it in MATLAB. So you can download it. It's free for everybody to use. And you don't need to get MATLAB installed in your laptops or in your computers to run it. We have an executable for you to use. So the intention is to use the CT scans and then generate some quantitative predictors or indexes to evaluate sample quality before running the test. So in a priori approach. So how this method works? So when we scan a tube, we have the mean CT value here, which is the first profile on the left-hand side. And then we are using statistical descriptors to get a little bit more information. In the center, you see the standard deviation based on these images. And on the right-hand side, you see the coefficient of variation. So how we can get this standard deviation and coefficient of variation is that when we scanned a specimen or an object in the CT scanner, we got 2D slices, so cross-sections images. And then when you open the metadata, what you see is a matrix with numbers. So we are basically calculating the homogeneity between these numbers or the heterogeneity between these numbers using the standard deviation and coefficient of variation. So if you open one of these 2D slices and then most of the numbers in this matrix are quite similar, means that the sample is homogeneous in its density, right? But if these numbers started to jump quite a lot, that is an indication of either the sample, the composition is different, or you have cavities, you have holes, you have heterogeneities. And this is reflected in the peaks in the standard deviation. So you see this analysis for the fixed piston sample, which is really good quality. And you see basically almost homogeneous profiles with a few peaks here and a few peaks there. What happens if we run the same thing on a Shelby sample? Well, this software also allows you to check the CT values in different locations. But what happens if we run the same analysis on the Shelby tube, which is this one on the left-hand side? Now you see strong peaks in the standard deviation and the coefficient of variation. And those numbers of coefficient of variation are crossing a limit value, which is 0.1. 0.1 is, according to, from a statistical point of view, represent a group of data which is representative of the soil to be tested. So if the coefficient of variation is lower than 0.1, in theory, the density estimated through this analysis is reliable and is representative of the soil. But if this number is higher than 0.1, then there are a lot of heterogeneities within the specimen that most likely will be created by sample disturbance. So again, the cross sections, you see that if you have cracks, you will be able to see it in those profiles. But how do we know that this method works? Well, if you use the app, you have the possibility to get profiles that you can download and then plot by yourself and include in any report you want to provide to the client. But how do we know that this works? Remember that I have discussed a few minutes ago about the index proposed by NGI, which is delta E by 0. We have done all this analysis long time ago for all the tests that we have done in Ballina, and we have also done all the CT scans. So we have reinterpreted those values using the CT scans, estimating the coefficient of variation for all of these samples we have previously tested. So what we can see is a trend saying that, remember the 0.1 coefficient of variation, below which the sample is assumed to be good quality, above which is assumed to be low quality. Well, if we correlate this coefficient of variation against the delta E by 0, which is the standard method based on mechanical test, you see that there is a good trend. So the method we are proposing now is a priori, so you don't need to wait until the end of the test to realize that your sample is good or bad. So the coefficient of variation can tell you before testing that your sample could be good quality or bad quality for testing. And these are results for Ballina clay that we have tested here in Australia for a long time, but also the silts from Spain that we have tested in the CRS and triaxial test. So what we are trying to do at the moment is try to engage with industry partners to try to use this method. And we have now an agreement with our CT scan health school of health in our university in order to run CT scans for commercial purposes. So if we have a client that is interested in checking the sample quality of tube specimens, the client can send us, ship the samples to us. We will run the scan for the client in our scanner here, and then we will ship the samples back to the client for testing. The only condition is that we would like to have at least one odometer test from each tube to be tested in our university to be able to put more points to this plot in order to prove that this method is good and it can be used for many different soils. All right. So the approach is based on this. So COV higher than 0.1 is in theory poor quality sample. Don't use it for mechanical testing. Lower than 0.1 is good quality. You should use it for mechanical tests and definitely for design. So the final take-home message is basically sample disturbance must be recognized for a process that we have many factors that may induce may have negative impacts on sample quality and therefore in soil properties. Shelby tube should be avoided. I strongly recommend don't use them just in the standard version. So you can use it for as part of the fixed piston samples. Fixed piston samplers should be used, is by far much better than Shelby tubes. In cases where there is room and money to use the mini Sherbrooke, we are more than happy to collaborate with industry, providing our block sampler for this type of jobs. And finally, we are proposing a new method that hopefully could be adopted by many practitioners, and we can try to, all of us, move forward to a better practice in Australia. All right. That's it. Thanks for listening to me, and I'm more than happy to answer questions about this topic.